Hi everyone. In this video, we are going to look at starting chapter 7, which is called the normal probability distribution. In 7.1, we discuss its properties. And in introducing that, we'll look at a kind of a little bit of a strange example, but we're going to talk about the uniform distribution. The uniform distribution, that was one where like everything has the same likelihood of outcome. And we'll look at we'll have a visual of this in a moment. But we start out with a scenario where, like, if you ever had a friend that's always late, like you're either that guy or you know that guy or girl, but a friend that's always late. So for me, growing up, it was my mom was always late. I never knew like how late she was going to be, but always late. Picking me up from football practice, my mom was late. If we had to go to an appointment, my mom was late. It was very frustrating, so I try to be very punctual as a person. But you might be that person. But we're gonna look. So that's the scenario. But we're gonna look at the uniform probability distribution. So go from that weird example, but apply it to the uniform probability distribution where any two intervals of equal length are equally likely. Okay, and so what does that look like? First of all, well, it looks like this rectangle. Okay, and so first, before we get to that little rectangle there, we'll define a probability density function is an equation used to compute probabilities of continuous random variables. So instead of discrete, we're talking about continuous random variables here. And it must satisfy two properties. The total area under the graph over all possible values of the random variable has to equal 1, and that's because we're talking about probabilities here, right? The sum of the probabilities of every outcome has to be 1 for it to be a probability distribution. So now with a continuous random variable that we're looking at a picture, a graph, the area under the graph has to be 1. Okay, so the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. Right? You can't have negative probabilities, so my graph cannot go below the x-axis. All right, so that's the setup for this visual. So what we're looking at in the picture, and let me zoom in on it a little bit here. What we're looking at in the picture is, if you see here in that example of my friend being late, there are always some number between 0 and 30 minutes late. Again, I don't know how many minutes late, but they're always late. So somewhere between 0 and 30 minutes late. And any two outcomes are equally as likely. So if I draw some lines here, so some poor vertical lines, here are two vertical lines that look like they might be between like 7 and 8 maybe on my x-axis. The probability of my friend being between 7 and 8 minutes late is just as likely as if I draw two other vertical lines over here. And those two, maybe those are between 21 and 22 minutes late. So the probability that my friend is between 7 and 8 minutes late has the same likelihood as the probability that my friend is between 21 and 22 minutes late. Or in the case of me growing up, it was my mom, like I said. So how do I actually compute that probability using this picture, this graph? Well, they're rectangles, so I know how to find the area of a rectangle. The area of a rectangle is base times height, right? So the base of that rectangle is 1 from 7 to 8, right? That's a distance of 1. And then the height of that rectangle, this guy over here on the y-axis says that the height of the rectangle is 1/30th. If you multiply 1 times 1 over 30, you get a probability or an area of 1/30th. But then we're going to apply the probabilities to that. So the probability that my friend is between 7 and 8 minutes late is the area of that rectangle, 1/30th. And that 1/30th is the probability that they're between 7 and 8 minutes late. It's also the probability that they're between 21 and 22 minutes late. So the two different outcomes are equally as likely. Okay, so that's because we have a uniform distribution. Now, in probabilities, they're not always uniform. We'll look at other distributions in a little bit, but this one is a uniform distribution. Still working with that same example of my friend being late, always late. What's the probability that they're between 10 and 20 minutes late? So now if I widen the interval, the probability that they're between 10 and 20 minutes late, well, again, the base of that rectangle from 10 to 20 is a distance of 10, and then the height of that rectangle is that y value of 1/30 10 times 1 over 30 is 10 over 30, and I could simplify that to 1/3, or I could write it as 0.33 repeating, or I could write that as 33 1/3%. I could write that a lot of different ways, okay? But the point of this example is to say, all right, you've computed areas before. We just spent a few sections talking about probabilities. Well, now we're going to interpret areas under curves as probabilities, as likelihoods. The area of that rectangle represents the likelihood of the outcome. That's the connection that I want you to fuse there. And now what it says at the top there, that's what I was just talking about, connecting probabilities and areas. But normal probabilities don't look like rectangles, right? They have different shapes. They may be skewed right, they may be skewed left, or the distribution we use most frequently is the normal distribution. This guy right here. We've seen that before, the bell curve, right? Remember talking about the bell curve earlier in the semester, back when you used to be able to see my face. So that's coming back, but now we're talking about the area under that bell curve. All right, and so what it says here, many continuous random variables have relative frequency histograms that have a shape similar to the normal curve, right? This is the shape. So heights of males, heights of females, blood pressure, heart rates, they all have that bell-shaped distribution. And a continuous random variable is normally distributed or has a normal probability distribution if the histogram looks like that of a normal curve, okay? Moving down a little bit here on my slide, let me drag my rectangle down. We have, this is kind of a how do you draw the normal curve. By the way, so I kind of go back and forth. It is a bell curve. It is a normal distribution. It is a normal curve. Those all mean this thing right here, normal distribution. When it comes, in terms of drawing it accurately, we have, we've drawn these before. The mu, the mean, is in the center, and then you add and subtract the standard deviation. But just if you want to draw it really precisely and accurately, where do I put that plus sigma and that minus sigma? Like, how far away do those get drawn from the center? Well, there's this term in math called an inflection point. And if you've taken calculus yet, I know many of you haven't, but maybe a couple of you have. But if you've taken calculus yet, that term should be familiar. But that's where the graph kind of switches, where it's up here, it's concave downward, like a caving downward, whereas over there, it's concave upward. Right, that point right here is where the graph switches concavity, and I'm not going to expect you to have these drawn perfectly when you draw them, but if you choose to, right, that's just going to make your graph look a little bit, your sketch look a little bit better. That's where you put your plus sigma and your minus sigma, okay? But that's what our curve looks like. Here are a couple of fairly basic examples of normal distributions and how changing the mean or the standard deviation affects the look. Right, in the one on the left here, I have a mean of 0 and a standard deviation of 1. That's the yellow normal distribution. Whereas if I keep the mean 0 and bump the standard deviation to 2, well, that takes that same distribution and spreads it out over a greater area. The tails still trail off in both directions, but with a standard deviation of 1, it's more packed together, whereas with a standard deviation of 2, it's everything is just more spread out. Okay, but because we're still talking probabilities, right? The area under the blue curve, the area under the reddish curve, those are both equal to 1. So they have equal areas. They represent 100% of the stuff underneath them. Okay, but one is more packed together, one is more spread out. In the example on the right, when I change the mean, really all I'm doing is shifting my distribution to the right or to the left. So standard deviations are both 1. Mean is 0, mean is 3. It's just moving my distribution over to the right or to the left. Then we'll have a list of some properties of our normal density curve. It's symmetric about the mean, right? That means you have the same on either side of the mean, the same amount of stuff. Because it's symmetric, the mean, the median, the mode, they're all in the middle, and the curve has that single peak The highest point is where is the mean, is in the center. Okay, what I just talked about, inflection points, when you add and subtract the standard deviation. Area under the curve is 1. That's important because we can talk about probabilities. And then if it's symmetric, the area to the right and the left of the mean both have to be a half, right? If there's 50% of the stuff to the left of the mean, 50% to the right. Okay. This next one is a little wordy, but it basically means you never touch the x-axis. As your variable increases without bound, gets bigger and bigger, the graph approaches but never touches the horizontal axis. Same on the other end as you decrease without bound. And that's just because really tall people exist, right? For every really tall 6'1" person like me, there's a 6'7" person in the NBA, and for every 6'7" person, there's still somebody that's taller than them. There's Manute Bol was an NBA player. He was like 7'6" or 7 inches tall, really tall, back in like the 70s or 80s. But that's why it never touches the horizontal axis, because there's always a possibility that one of those extreme outliers exist. Okay, and then another term that coming back from earlier in the semester, the empirical rule applies to this distribution. So where we have 68% within 1 standard deviation, 95% within 2, 99.7 within 3 standard deviations of the mean, and then just to have, let me scroll down a little bit here and drop that rectangle off. There we go. Just to refresh you on this guy here, there we go. We have our normal distribution, and these are all the percentages applied to it. Although, as we go through Chapter 7, we will have a much more precise and accurate normal way of computing probabilities under our normal curve. So you'll stay tuned in a later section to see how that works. In this next example, we have a table on the right. The table on the right gives the heights of 200 3-year-old female patients at a pediatrician. So 200 little 3-year-old girls, and their heights are calculated, and then we have the relative frequency of those 200 3-year-old girls. All right, and if you punch all that into Minitab, you can find the mean and the standard deviation. 38.72 is the mean, and 3.17 is the standard deviation. Okay, so this is you can pause the video if you want, take a look at the table. The height in inches is given on the left. The frequencies, the relative frequencies are given on the right. And then we also have at the bottom here a normal curve laid on top of a histogram. So if I take the mean of 38.72, standard deviation of 3.17, that generates this blue normal curve. 38 is in the center, and then add the standard deviation, you go out here, subtract the standard deviation, you go out there, and you can, if you want, in your calculator, type in, what is 38.72 plus 3.17, 38, 39, 40, 41, almost 42, and that puts me about there for 1 standard deviation away. Subtract the standard deviation, 38.72, 38, 37, 36, 35, about 35 and a half maybe. That puts me right about there for 1 standard deviation below the mean. 68% of those 3-year-old females are represented between those 2 standard deviations. Okay, so we can see that the histogram kind of fits nicely underneath that bell curve. Not perfectly, but fits pretty accurately. It's well represented by that curve. All right, and then what the problem actually says is compare the area of the rectangle for the heights between 40 and 40.9 inches to the area under the normal curve for heights between 40 and 40.9 inches. And it's highlighted green there for us. Let me just draw an arrow pointing to where I'm looking at right there. So right there, we're saying compare the area of that rectangle. And the area of that rectangle comes over here from this 0.11 on the distribution. Okay, the area of that rectangle, compare that to the area under the normal curve. And are they perfect? The answer is no, but are they pretty darn close to each other? Well, I have this like little sliver out there that is bigger, and then this little missing sliver under there that kind of cancels out some of that, but they're pretty close to each other. So the area of that rectangle is probably pretty darn close to 0.11. And again, we're connecting an area of, in this case, a rectangle, to a relative frequency, which we can then interpret as a probability. What's the probability that a 3-year-old female is between 40 and 41 inches? About 11%, according to this data. Okay, first, on this next slide, take a look at this terrifying formula at the top. This we will never use. Don't worry. Okay, this is the formula, the function, the probability density, or the normal probability density function, and it looks terrible. Know that it exists. You don't even have to know it exists. Well, I'll probably never mention it again in this class. It exists. It's a function. It's one that we won't use. We're going to use the graph. We're going to use a table to compute normal probabilities. Because it makes much more sense than using that ugly function. But what I want to talk about in this slide is if I have a random variable x that is normally distributed, the area under the normal curve for any interval of values of x represents either, ready? All right, so these two highlighted things here are the two different ways that we can interpret this area, the area under my bell curve. We can interpret it, one, as a proportion of the population with the characteristic described, or number two, as a probability that a randomly selected individual from the population will have the characteristic described. And we'll look at an example in a minute where we talk about both interpretations. But these are the two ways that we can, the two types of questions that we can ask or answer using our normal curve. We can talk about proportions or probabilities. All right, so this is the last example for the section, and we'll actually get to do a little bit of math here. I know, sounds crazy, but we have total cholesterol for males aged 20 to 29 is approximately normally distributed with a mean of 180 and a standard deviation of 26.2. Part A wants us to draw a normal curve with parameters labeled. All right, so what does that mean? Well, what I'm going to do to draw my normal curve is I'm going to draw a, oops, I don't want to be on my highlighter. I'm going to draw a horizontal line and then try my best to draw a nice looking normal curve above it. Sometimes it looks good, other times it looks bad. I have an undo button, so I have an infinite number of times that I can try this out. I don't mind that one, but I'm going to give it one more shot. There, that looks pretty good. Not perfect, not ideal, but decent enough for this example. Okay, so once you have your curve drawn down the center, I'm going to drop a center line here. I don't have to draw that line in, but it helps me. I'm going to label my mean, which is 180. Then I'm going to go out here to one standard deviation away, and I'm going to add and subtract that 26.2. Now, 180 plus 26.2 is 206.2. 180 minus 26.2 is 160, 153, 153.8. That is mu minus sigma and mu plus sigma. If I add my standard deviation again, I'm going to appear 2 standard deviations above the mean. That would be 232.4. That's mu plus 2 sigma. And then I can go 2 standard deviations below the mean. If I take 180 and subtract double the standard deviation, I get 127.6. That is mu minus 2 sigma. I could go 3 standard deviations out. It gets a little bit messy if you try to go to 3, and you can. It's perfectly fine. But let's see what I get for 3 standard deviations away. I got 101.4. And then if I add and go 3 standard deviations above, 258.6. Okay, so that's part A done. Draw my normal curve. Part B, an individual with a total cholesterol greater than 200 is considered to have high cholesterol. That's bad. So where is that? Shade this region under the normal curve. Let's say it's about right there would be 200. If this is 206 right there, then if that's 206, then 200 would be just a little bit below that. I'll put a little 200 there. Okay, shade this area under the normal, this region under the normal curve. So that's everything to the right because it says in the problem greater than 200. There we go. All right, so that's what we're looking at. All right, everything to the right of 200 represents someone having high cholesterol. Now, part C says, give two interpretations of this area. This goes back to the previous slide where we can interpret that area as a proportion or as a probability. Okay, so it helps in understanding this interpretation if we throw a number on this. So let's just say that this area, and this I'm just pulling a number out of nowhere. Let's say that that area is 0.15. Okay, so if that area is 0.15, what does that mean? Let me scroll up a little bit, and we see a white background instead of green. So what does that 0.15 mean? 0.15, or actually let me write it this way. The proportion of individuals with high blood pressure is 0.15 or 15%. Okay, that's the one interpretation. So 15% of the population, and what is the population? I should have even included that in my sentence. This is males age 20 to 29. So maybe instead of individuals, I should have said there males 20 to 29. So the proportion of males 20 to 29 with high blood pressure is 15%, according to the number that I made up. That's what that blue shaded area represents. That's one interpretation. Okay, then the other one is using the word probability, as a probability. The probability of a randomly selected male age 20 to 29 having high blood pressure is 15%. Okay, that's the other way to interpret that blue shaded area. But the important thing is we're connecting the area under the curve being either a proportion, a part of the population, a fraction of the population, if you will, or a probability that a randomly selected person has that characteristic. In this case, it's high blood pressure. Okay, so that's the end of the section. You should start working on this homework now, and if you have questions, please email me, ask me questions, use the MyMathLab help tools, all the things that are at your disposal. Thank you for listening. Bye.